To ensure consistency and repeatability, modern DevOps teams use infrastructure as code. The infrastructure as code means that the infrastructure is defined and managed using code, allowing for version control, automation, and collaboration. F5 provides tools and frameworks to help you implement infrastructure as code in your environment. In this chapter, we will explore the key concepts of infrastructure as code, its benefits, and how it can improve team collaboration. We will also discuss the automation tools available for implementing infrastructure as code and provide an example pipeline for deploying F5 BigIP configurations using Terraform and Ansible. Infrastructure as code offers several key benefits that enhance the management and deployment of infrastructure. These benefits include consistency. Infrastructure behaves identically across environments. Repeatability. Deploy and redeploy environments reliably. Transparency. Track changes via version-controlled code. Collaboration. Facilitates teamwork through shared repositories and reviews. Speed. Increases the speed of deployments by reducing manual steps. Elimination of configuration drift ensures that the actual state of infrastructure matches the intended configuration. Security automates security checks and compliance validation. Infrastructure as code improves team collaboration by making infrastructure configurations version-controlled, transparent, and accessible to all contributors. By working with infrastructure as code, teams can collaborate more effectively, share knowledge, and ensure that everyone is on the same page regarding infrastructure changes. Key collaboration benefits include shared visibility. Everyone sees and understands infrastructure changes in code. Pull request workflows. Changes are proposed, reviewed, and approved before deployment. Cross-functional alignment. Developers, ops, and security collaborate on the same codebase. Faster onboarding. New team members learn from existing code and commit history. Living documentation. IaC replaces outdated docs with accurate, up-to-date definitions. This collaborative foundation helps teams move faster, avoid miscommunication, and ensure that infrastructure changes are well understood and agreed upon by all team. To implement infrastructure as code, teams often use a combination of tools. These tools help standardize and automate the provisioning and configuration of systems and network devices. Check out the official F5 GitHub repository before you start. It contains a lot of resources, including templates, modules, and examples for automating F5 BigEP deployments using infrastructure as code. Common automation tools include Ansible, Terraform, Chef, Puppet, AWS CloudFormation, and other environment-specific tools. By using these tools, you can automate the entire lifecycle of your infrastructure, from provisioning to monitoring and operating stages. Most organizations use a CI/CD pipeline to automate the deployment of F5 BigIP configurations. This pipeline typically includes stages like validating, planning, deploying, and post-actions. In this example, we show a pipeline that automates the deployment of F5 BigIP configurations using Terraform and Ansible. In the lint and validation stage, the pipeline first checks the formatting and structure of the code using tools like tflint and Ansible lint. Then it runs Terraform init to prepare the environment and Terraform validate to confirm the configuration is correct. All infrastructure as code setups should include these pre-checks from the start to catch mistakes early and ensure the configuration is safe. The validation stage can include scanning the code for risks. These checks help identify security issues in Terraform and Ansible files before any deployment takes place. This stage can also include checks for compliance with organizational policies, helping teams enforce required configurations and prevent misconfigurations. Next is the plan stage. Here, Terraform plan is used to create an execution plan. The output can be reviewed by the team to verify what changes will be made. This plan output can also be automatically posted as a comment in the pull request, allowing reviewers to see the proposed changes directly in the code review workflow. In the deploy stage, the pipeline uses Terraform apply to make the changes. Ansible then applies the configuration to the BigIP system using a playbook. These deployment steps can be configured to run manually or automatically, depending on the organization's review process and risk tolerance. Finally, the pipeline can include a post-action stage. In this stage, notifications can be sent after deployment. These notifications might go to a team chat channel like Microsoft Teams or Slack, or they might create an incident to ensure visibility of the deployment outcome. Automation eliminates the errors and delays caused by manual processes. Working with complex systems like F5 BigIP can be challenging, especially when managing multiple environments. Infrastructure as code makes deployments faster, reduces downtime, and helps teams deliver services and applications on time. IaC reduces complexity and improves flexibility by providing a clear, version-controlled way to manage infrastructure. As part of a DevOps toolchain, IaC helps ensure teams follow the same standards and practices, improving quality and collaboration across the development and operations lifecycle. This chapter explains how to automate API endpoint protection using BigIP Application Security Manager with OpenAPI schema validation. Modern applications frequently update their APIs. If a security policy is not updated at the same time, these changes can leave the application open to attacks. Updating policies manually every time an API changes is slow, easy to get wrong, and hard to manage when applications change often. Automating the API protection process makes sure that BigIP always uses the latest API information. This reduces manual work, cuts down on mistakes, and keeps the application secure. To understand what the automation will replace, first look at the manual process. This is a test application that supports OpenAPI. However, it has undocumented internal routes that should not be exposed. The goal is to protect the application using BigIP Application Security Manager. Start by opening the BigIP web interface and navigating to Application Security, then Security Policies. Then we click Create a New Policy. In the form that appears, we fill the name of the policy, select the template, and upload the OpenAPI file. This file contains the API schema and defines which routes are allowed. Then we select the virtual server where the policy will be applied. Set enforcement mode to blocking and click Save. Now the policy is created and we can test it. Go back to the application and refresh the page. The application should now be protected by BigIP. It returns a JSON response with a support ID. This shows that internal routes are hidden and only public API routes are accessible. This manual setup is what the automation will replace. To automate protecting APIs on BigIP, we use a simple Ansible playbook. The Ansible playbook does three things. First, it uploads the OpenAPI, also known as Swagger, file to BigIP. This file defines the API structure, including available routes and operations. Second, it creates a new security policy or updates an existing one on BigIP. The uploaded Swagger file defines which API routes are allowed. This ensures that only the correct routes are protected and exposed. Third, it attaches the updated security policy to the correct virtual server. This means the application traffic is immediately protected without needing to wait or perform extra steps. All of these actions are described and automated in the provided Ansible playbooks. This approach removes the need for manual configuration through the BigIP web interface. Now let's look at the Ansible playbook in action. This is the playbook that automates the process of uploading the OpenAPI file and creating a security policy. It contains tasks to upload the OpenAPI file using iControl REST API and create a new security policy. The playbook also attaches the policy to the correct virtual server. Next, we open the BigIP web interface and navigate to Application Security and refresh the page to make sure the policy does not exist. Then we run the Ansible playbook and wait for it to finish. The playbook will upload the OpenAPI file and create a new security policy. Once the playbook is completed, we go back to the BigIP web interface and refresh the page. We can see that the new security policy is created and attached to the virtual server. Then we go back to the application and refresh the page. The application should now be protected by BigIP. It returns a JSON response with a support ID. We also check another route that included in the OpenAPI file. This route should return a 200 OK response. This confirms that the playbook correctly updated the API protection based on the latest schema. Now it's time to fully automate the process and trigger the pipeline on each commit into the main branch. To set up GitLab CI/CD pipeline, create a GitLab CI YAML file in the root of your project repository. This file defines the stages and steps that GitLab Runner will execute. Begin by defining a simple pipeline with a single stage called deploy. Inside this stage, you will run a command that executes an Ansible playbook. The playbook will upload the new OpenAPI file and update the BigIP API protection policy. It uses an inventory file and passes extra variables for authentication. The job triggers only when changes are pushed to the main branch. Make sure GitLab Runner has access to your big IP instance and necessary credentials are set up properly. With this setup, every time a developer updates the API and pushes to the main branch, GitLab automatically updates big IP without any manual action. This ensures that API security policies always match the application. We're continuing with the GitLab pipeline demo. On the screen, we can see the GitLab pipeline configuration file. It defines the deploy stage, installs Ansible, and runs the script that executes the Ansible playbook. It also passes in the necessary variables, including the big IP credentials. Now, we open the Swagger file and make a change. In this version, we're adding new routes for user registration that weren't included in the previous version. Next, we commit the changes and push them to the main branch. This triggers the GitLab pipeline and starts the deployment process. The pipeline takes a minute or two to complete. Once it's done, we can check the GitLab console output. We can see that the Ansible playbook ran successfully, and the new security policy was applied to the big IP instance. Now we switch back to the big IP web interface and go to the allowed URLs section. We can see that the new API routes are listed here, confirming that the playbook correctly updated the API protection based on the latest Swagger file. To recap the process, we started with a manual setup of API protection on big IP. Then we automated it using Ansible playbooks to upload the OpenAPI file and create a security policy. Finally, we set up a GitLab CI/CD pipeline to automatically trigger the deployment whenever changes are made to the OpenAPI file. You can use this example as a starting point to build your own CI/CD pipeline for API protection on big IP. Feel free to customize it based on your specific needs and environment. The pipeline can also be extended with additional stages, like testing or notifications. It's easy to integrate it with tools like Slack or Microsoft Teams to send alerts when deployments are completed. And finally, remember to test your pipeline thoroughly before using it in production. Also, keep your OpenAPI file up to date to make sure your application stays protected against the latest threats. In this chapter, we will show how to set up infrastructure configuration using Terraform, Ansible, AS3, and iRules. When working on important projects, it is critical to test changes before they are deployed to production. We will use a Jenkins pipeline to create and manage the environment. To test changes, we will use a dry run to validate the deployment and update the pull request with the results. We will create infrastructure in AWS using Terraform, allowing us to manage resources as code and track all changes through source control. Once the infrastructure is provisioned, Ansible is used to deploy AS3 declarations and iRules to big IP instances. This approach guarantees that configurations are consistent, automated, and easily auditable across all environments. We start the demo from the GitHub repository, where we have the code for our project. In the root folder of the repository, we have a Jenkins file that defines the pipeline. The pipeline contains several stages that will be executed in order. The first stage checks the branch and detects if we need to run the pipeline. The pipeline will run only if the branch is main or if there is a pull request into the main branch. This allows us to run the pipeline only when we need to test or apply changes. The second stage clones the repository and checks out the branch. This allows us to work with the latest code and test the changes. The third stage is about Terraform. We use Jenkins credential storage to store the AWS credentials. This allows us to use the credentials in the pipeline without exposing them in the code. Then we use the Terraform init command to initialize the environment. This command downloads the required providers and sets up the backend for storing the state. In our case, the state is stored in Terraform Cloud. On the pull request, we run a dry run to validate the changes and save the Terraform output. On the commit to the main branch, we run a full deployment. This allows us to test the changes before they are applied to production. After the Terraform stage, we have a stage for generating the Ansible inventory. This stage generates an Ansible inventory file based on the Terraform output. The inventory file contains the connection details for the big IP instances that we will configure. Next, we have an Ansible stage that deploys AS3 and iRules to big IP. Here, we use the generated inventory file to connect to the big IP instances and deploy the AS3 declarations and iRules. On the pull request, we run a dry run to validate the changes as we did with Terraform. And on the commit to the main branch, we run a full deployment. Then we have a stage that updates the pull request with the results of the deployment. This allows us to see the results of the dry run. In our example, we post a list of destructive changes that will be applied to the infrastructure. This allows us to review the changes carefully and prevent any accidental changes to the infrastructure. Finally, we have a stage that indicates the end of the pipeline. This stage is used to notify the team that the pipeline has finished running. In our case, we send a notification to the output, but you can also use other notification methods like email, Slack, or Microsoft Teams. Let's see how this works in practice. We move to Jenkins, where we will create a pipeline for our project. We set the name and select multi-branch pipeline as the type. Next, we click OK to proceed to the next step. Then we set the display name for our pipeline and move to the repository section. From the drop-down, we select GitHub as the source. Now, we need to provide credentials to access the repository. We can either create new credentials or use existing ones. Then set the repository URL. We can leave other settings as default. Finally, we click Save to create the pipeline. Jenkins will automatically scan the repository for branches and pull requests. Once it's done, we can see the branches and pull requests in the Jenkins dashboard. We can also see the pipeline status for each branch and pull request. This is useful to track the progress of the pipeline and see if there are any issues. Now let's test the pipeline by making a disruptive change to the infrastructure. We create a new branch and make a change to the workloads TF file where we remove one of the workloads. Then we commit the change. As we can see, Jenkins automatically detects our commit message, but the pipeline is skipped because the branch is not main. Now we open the pull request into the main branch. To do that, we go to the root folder of the repository, click on Compare and Pull Request, and create a new pull request. We set the title and description, and then we click Create Pull Request. We see that there is a message displaying that some checks haven't completed yet. This means that Jenkins is still running the pipeline. We go back to Jenkins and open Pull Request tab. On the dashboard, we can see that the pipeline is running. So we click on the pipeline to see the details, then we click on the job name and open the pipeline overview. Here we can see the stages of the pipeline and their status. We can see that some of the stages are still running, while others are already completed. Now the Terraform init and action stage is running. This stage initializes the Terraform environment and downloads the required providers. Once it is completed, the Terraform plan step will be executed. This stage generates a plan for the changes that will be applied to the infrastructure. It shows the resources that will be created, updated, or destroyed. After some time, we see that the Terraform init and action stage and rest of the stages are completed, which means that the pipeline executed successfully. Now we go back to GitHub to check the pull request. We see that the pull request is updated with the results of the pipeline. The comment shows the list of destructive changes that will be applied to the infrastructure. This allows us to review the changes carefully and prevent any accidental changes to the infrastructure. Next, we merge the pull request into the main branch. This will trigger the pipeline again, but this time it will run a full deployment. We go back to Jenkins and see that the pipeline is running again. We click on the pipeline to see the details, and then we go to the pipeline overview to see the execution process. After some time, we see that the pipeline has finished and all stages are green. So we successfully removed the workload from the infrastructure. What are AS3 and I rules? Application Services 3 is a declarative API provided by F5 to configure application delivery and security services on big IP devices. It makes deployment easier by letting users describe their setup in a simple JSON format that can be reused, shared, and automatically applied the same way every time. An I rule is a powerful scripting language used on big IP to control traffic behavior dynamically. I rules can inspect, manipulate, and direct traffic based on customizable conditions. They are typically used for load balancing decisions, content-based routing, security enforcement, and application optimization. How does deployment work with Ansible? Deploying AS3 declarations and I rules is typically managed through automation tools like Ansible. An Ansible playbook is used to render AS3 JSON templates containing virtual server, pool, and monitor configurations, along with associated I rules. These templates are dynamically populated using variables provided by Ansible inventory or variables files. Benefits of deploying I rules with AS3 using Ansible. Declarative management. Makes it easier to set up and avoid mistakes by using simple JSON files to describe your setup. Version control. You can track changes to iRules, review them, and go back to earlier versions if needed. Automation compatibility. Can be integrated into CI/CD pipelines. Consistency. Your setup is the same in every environment. Overall, using AS3 and Ansible to deploy iRules makes automation easier and more consistent, but it still needs some upfront setup and regular care to keep things simple and running smoothly. Let's look at the AS3 and iRules deployment in more detail. We have a simple Ansible playbook that deploys AS3 declarations to Big IP. The playbook renders the AS3 template and uploads it to the Big IP instance using the iControl REST API. This is the template that we use to render the AS3 declaration. It contains the configuration for the application services, including the virtual servers, pools, and monitors. It also contains the configuration for the iRules, using a loop to create multiple iRules. This is an iRule example. It contains a simple log message that is printed when the iRule is executed. When we create a new iRule, we can simply put it into the iRules folder, and it will be automatically picked up by the Ansible playbook. This allows us to easily add new iRules to the configuration without changing the playbook. The process is the same as in the previous demo. We create a pull request with the changes to the iRules. Jenkins will automatically detect the pull request and run the pipeline. The pipeline will perform a dry run to validate the changes. Then we can review the changes in the pull request. After that, we can merge the pull request into the main branch and run a full deployment. Because we don't have any infrastructure changes, the Terraform stage will not make any changes to the infrastructure. It will only generate the Ansible inventory file and pass it to the next stage. Then, the Ansible stage will deploy the AS3 declarations and iRules to the Big IP instance. As we can see, the pipeline completed successfully and all stages are green. To test the changes, we can go to the Big IP web interface and check the iRules. Let's open the new iRule and confirm it contains the log message we added. The key takeaways from this chapter are the importance of collaboration and a well-defined process in managing infrastructure and application configurations. Collaboration works best when everyone follows the same process. Automation tools like Jenkins help teams test changes, see results, and follow the same pipeline. Each step shows clear status messages, so it's easy to spot problems. Using Git with pull requests means every change is tracked, reviewed, and approved before it's merged. Terraform keeps infrastructure in version-controlled code. With Terraform Cloud, teams avoid conflicts and track changes easily. Ansible uses dynamic inventory from Terraform outputs to deploy AS3 and iRules to the right Big IP instances. When used together, these tools make the process predictable, reduce errors, and help teams reuse the same config across environments. It also makes collaboration much easier and standardized. There are many discussions about the source of truth in automation. In this module, we will look at how to store and manage state for Big IP devices by using Terraform. We will also cover recommendations for managing the state file, including how to store it securely and how to avoid common pitfalls. When using Terraform with F5 Big IP, it is crucial to manage the state file properly. This includes storing it securely, keeping it up to date, and ensuring that it is not modified manually. Let's start with the basics of Terraform state management. Always store the Terraform state remotely with encryption enabled. Use backends that support state locking and versioning to prevent data loss and enable collaboration. Treat the Terraform configuration and its associated remote state as the only source of truth. Never make manual changes directly to the infrastructure. Prefer replacing over modifying critical resources to avoid configuration drift and unexpected behavior. Apply strict security controls. Validate that backends, access credentials, and automation pipelines meet organizational security, compliance, and auditing standards. Use role-based access control, encryption in transit and at rest, and secret management solutions. Enable logging at the backend and monitor changes to infrastructure resources. When using Terraform, the state file is the source of truth. It contains the current state of your infrastructure and is used to determine what changes need to be made. Always use Terraform to create, update, and delete resources, and avoid making manual changes directly on Big IP. Manual changes can lead to configuration drift, making it harder to manage and recover your infrastructure. To ensure that the state file is always up to date, use a version control system like Git to track changes to your Terraform code. This allows you to roll back changes if needed and provides a history of changes made to your infrastructure. In addition, store the state file in a secure remote backend, such as Terraform Cloud, AWS S3 with DynamoDB, Azure Blob Storage, or Google Cloud Storage. This allows for easy access and management of the state file, while also providing security features like encryption and versioning. The workflow for managing the state file should look like this. All changes must start with a git commit and pull request. A CI/CD pipeline should run Terraform FMT and Terraform validate to check the code, then run Terraform plan and post the plan output in the pull request. Before merging, require pull request approvals. Review the Terraform plan output to verify changes. Apply security policies using Sentinel or Open Policy Agent to block dangerous configurations, such as 2 open IP addresses. Once approved, the pipeline applies the Terraform plan and updates the remote state. Run drift detection regularly using Terraform plan with the detailed exit code flag. Send alerts if any drift is found. Do not make manual changes on big IP. Manual edits cause drift, break state tracking, and complicate recovery. This workflow ensures that all changes are tracked, reviewed, and approved before being applied to the infrastructure. It also helps to maintain a clean and organized code base, making it easier to manage and troubleshoot any issues that may arise. To keep your Terraform state and infrastructure secure, follow these recommendations. Use a remote backend with encryption and versioning such as AWS S3 with server-side encryption or Terraform Cloud. Encrypt the state file at rest and in transit to protect from unauthorized access and sensitive data loss such as access keys and passwords. Manage secrets properly. Use Vault, AWS Secrets Manager, Azure Key Vault, or GCP Secret Manager. Use least privilege access. Only give service accounts the permissions they really need. Enable audit logging on S3 and send big IP logs to a SIEM system like Splunk or ELK. Always encrypt communications. Use HTTPS, encrypt your state file, and make sure Big IP management uses TLS 1.2 or higher. Use Terraform Sentinel or Open Policy Agent to enforce security policies. This helps ensure that your infrastructure meets your organization's security standards. Use approved Terraform modules to standardize your infrastructure. This helps ensure that your infrastructure is consistent and easy to manage. Use Terraform state locking to prevent concurrent changes. This helps avoid conflicts and ensures that only one person can make changes at a time. These recommendations are important for keeping your infrastructure secure and compliant. By following them, you can reduce the risk of security breaches and ensure that your infrastructure is always in a known and secure state. Terraform can use different backends to store the state file. The backend you choose can affect the security and reliability of your infrastructure. Always pick a backend that supports encryption, locking, and versioning. The first option is to use Terraform Cloud or Terraform Enterprise. These services are designed for teams and provide built-in locking, secure team workspaces, and policy enforcement. They also offer features like versioning and access control, making them a great choice for managing your Terraform state file. For AWS users, S3 is a popular choice. It supports server-side encryption and versioning, which helps protect your state file. You can also use DynamoDB for state locking, which prevents multiple users from making changes at the same time. This is important for avoiding conflicts and ensuring that your infrastructure remains stable. Azure Blob Storage is another option. It supports Azure AD integration and immutability locks, which help protect your state file from unauthorized access and changes. Google Cloud Storage is also a good choice. It offers encryption and bucket lock features, which help secure your state file and prevent unauthorized access. Remember that the backend you choose should meet your organization's security and compliance requirements. Always confirm your choice with your security team. Here is an example of using AWS S3 for your backend. As you can see, we are using the encrypt option to ensure that the state file is encrypted at rest. We also specify a DynamoDB table for state locking, which prevents concurrent modifications to the state file. Here is how it looks in the AWS console. Here you can see the state file stored in the specified bucket and key. The encryption and versioning enabled to keep track of changes. In the DynamoDB, you can see the table used for state locking. This table prevents concurrent modifications to the state file, ensuring that only one person can make changes at a time. This simple setup provides a secure and reliable way to manage your Terraform state file, while also allowing for easy collaboration and version control. In conclusion, managing the Terraform state file is crucial for successful automation with F5 Big IP. Remember to store state remotely, securely, and with a solid plan for managing the source of truth across your infrastructure.